Hey everybody, it's Tuesday, November 10th. As you can see here in the aim today, our goal for today's video is going to be all about how we can apply concepts from the ATWOOD'S machine problem we looked at yesterday to the tabletop ATWOOD'S machine. As we said yesterday, the ATWOOD'S machine is a device that is used to demonstrate concepts of Newton's laws. And the thing I like about the ATWOOD'S machine, number one, is there are a lot of good conceptual questions that can be asked about it. And so you can definitely expect it to see it heavily featured on my tests as well as the AP test. But what's also great about an ATWOOD'S machine problem is it is a really good representation for the kinds of forces problems that you have to solve in this course. Now, if you remember when I started talking about Newton's laws this year, I said, we are going to talk about Newton's laws of motion, and that's all going to be pretty straightforward. You're going to remember a lot of that. And then eventually, we are going to get to a set of problems which are totally different from the problems that you've seen in the Regents physics class. And so the idea for these problems is essentially what makes them different is that you have to make up the equation that you're going to use to solve it. And the way you make it up is what we saw in the video yesterday. You draw a diagram of the forces acting on the object, which we call a free body diagram. You write the equations from the free body diagram, and then you solve those equations simultaneously. And so the main thing to realize here is the tabletop ATWOOD'S machine problem, which is pretty similar to a regular ATWOOD'S machine. I think you'll realize that when I show you the picture of it. The main thing that you need to know about it is that the way we are going to solve it is pretty much the way we solved an ATWOOD'S machine, just like a regular old ATWOOD'S machine. And the reason why we are going to solve these problems very similarly is not just because they are very similar, which they are, that's true. But the reason why we are going to solve these problems very similarly is because this is how you solve all dynamics problems. No matter what in this unit, now for the rest of this unit, the way we are going to be solving these problems is going to be exactly the same. We are going to draw a diagram of the forces. We are going to make up an equation. And then we are going to use those equations to solve for whatever we are asked to solve for. And so because that's like the whole ball game here, that's our first note of the day. The main method for analyzing the tabletop ATWOOD'S machine is exactly the same as the method for analyzing the traditional ATWOOD'S machine. And just so we're all clear about it, we'll write it right here. We draw the free body diagram. We write our equations. And then we solve. That's it. No matter what kind of dynamics problem we're actually talking about, that's the way we're going to do it. And that's an important thing to keep in mind. I'd like you to take a second to pause this video here, write that down, and when you hit play, we'll take a look at the actual setup here. Okay, so the tabletop ATWOOD'S machine problem, first of all, the tabletop ATWOOD'S machine is not like an official name for it. It's just what I call it to differentiate it from the regular ATWOOD'S machine. It looks like this. And so in a tabletop ATWOOD'S machine problem, we have an object sitting on a tabletop, hence the name, attached to a rope. That rope is, of course, draped over a pulley. And then that pulley is basically redirecting the force here, and the rope is attached to another object, which is hanging over the edge of the table. Here, it's not really shown, but here would be the edge of the table. And so I'd like you to take a second to sketch that in your notes. And while you are sketching that in your notes, I want you to think about the answer to a pretty easy question, I think. Let's say you were sitting below object B and you were holding it up, and then you let it go. Which way is object B going to move? If object B is going to move that way, which way is object A going to move? Should be pretty clear, right? But obviously having an understanding for how this thing is going to move is going to make our lives a lot easier when it comes to actually analyzing the situation and solving the problems. And so we want to make sure that we're good with that. So let's take a look. Hopefully you made that sketch. It's a pretty easy thing to draw. I don't want you to go nuts. It's not an art contest. Just like a quick little sketch will be good enough. I want to take a look at a simulation showing how these things are going to move, because then we'll be able to actually go ahead and solve the problem. And so the simulation here is going to look something like this. So we have here two objects, the one hanging over, the other one sitting on top of the table. And the first thing I want to point out, and actually we should go back and draw this in the drawing before we even look at this, is that this table for right now, just because we haven't talked about it yet, this table is frictionless. When we go and talk about friction, which we're actually going to start tomorrow, we are going to revisit this problem when there's friction. But because we are in a situation where we haven't discussed friction yet, we're going to do this for a frictionless situation. And so notice there's a slider here in this particular simulation for the coefficient of friction, and we're going to say that that is 0 for now. The other thing I want to point out while we have this thing open, let's just get rid of that, is that you can change the masses of these objects, and because this surface is frictionless, it doesn't actually matter if the object that's hanging is smaller than the object that's on the table. I have a general sense after teaching this for a number of years that that's a misconception that kids have. Probably because so much of your everyday life is spent dealing with situations where there is friction. As it turns out, that's actually true. When there is friction, if M1 is a lot smaller than M2, as it's shown in this particular configuration, then the object might not move. But because the situation is frictionless, basically no matter what, the system is going to move. And so the purpose of viewing the simulation really is just to get a sense of how these objects move. What I asked you to predict while we were drawing these things was, well, how are these things going to move? And the answer here should be fairly straightforward. But of course, let's just take a look at it. You guessed it, of course, because the force of gravity is acting on M1 and it's down, then we would expect to see M1 move down. And because the rope that M1 is attached to M2, M2 is going to get pulled over to the right. Now, I just want to point out here that it doesn't matter if M1, in this case the hanging mass, is way smaller than M2, the one on the table, because even if we do that, the system will still move. It's just it doesn't accelerate very much. But that's the idea. We expect M1 to move down. We expect M2 to move over to the right, and that's exactly how it ends up working. And because the main method for analyzing this situation is exactly the same as the main method for analyzing the situation for a regular ATWOOD'S machine, we might as well just go ahead and solve this thing. So let's take a look at a problem. This problem says, if the mass of object B, which I'm going to call M2, I know that was actually the opposite of what they just showed in that video, but we almost always call this one M2. So M2 is the hanging one in this situation. If the mass of object B, M2, is 35 kilograms, and the mass of object A, which we're going to call M1 here, is 15 kilograms, then we are being asked to determine the acceleration of the system and to determine the tension in the rope. And as we mentioned, the main method of analysis for this problem is the same as the method of analysis for the regular ATWOOD'S machine. So the first thing you have to do is you got to draw the free body diagram. And because now we've had experience with that for a number of days, I want you to pause this video and take the opportunity to try to do that on your own. So go ahead and pause this video here for about 2 minutes and draw the free body diagram for M1 and M2. And when you're finished with that, hit play and we'll go over it. Okay, so we'll make a label here for M1 and M2, and we'll draw those free body diagrams. So the first thing we'll do is we'll recognize that M1, which is the mass on the table, is going to accelerate to the right. I want to draw that up here because remember, it's like actually really important that you don't make that part of the free body diagram, that you put that separate. And so I'm just going to leave it all the way up there. And so I'm going to draw my box, and at the center of my box, I'm going to put a dot because that's almost always the way they show it on the AP test. They have a dot, and you draw the arrows from that dot. The biggest mistake I would guess that people might have made with the free body diagram for this object is forgetting that there are actually 3 forces acting on this object and not just one. So the first force that should be the most obvious to everybody that's really going to matter here is the tension in the rope. And because the rope is pulling this object to the right, we'll draw the tension going to the right. Of course, the object has a gravitational force acting on it straight down. And because this is object 1, we're going to call that M1G. You could label this FG1 if you want, but we might as well just start labeling it MG, because when we get to the equation part of this, that's the term we really want to end up using anyway, so we might as well not like make an extra step for ourselves. And then, of course, because this thing is sitting on a surface and the surface is exerting a force on the object, we have a normal force acting on the object as well. And because the normal force here is basically just going to cancel out the weight because the object is on a flat horizontal surface, we want to draw those arrows the same length. You don't have to write this, but just as a little side note for here, whenever an object is on a flat horizontal surface, it's very important to remember the normal force is equal to the weight. And so our free body diagram looks like that, and that's really it. Now, the more important diagram, perhaps, because in this diagram everything matters, is the diagram for M2. M2 is a little bigger, so I'll draw the box a little larger, although that doesn't really matter. And we'll say that this thing is accelerating down here, which it is going to. The first thing that we have is our tension. And the main thing you need to know about the tension, remember, is that the AP test actually gives you a point for making these arrows the same length. And so you want to make sure that you try your best to draw these arrows the same length. Obviously, when there's a grid space, that becomes like the easiest thing in the world. But because the tension in the rope is constant, you have to draw these arrows the same length. That part is very important. And then we'll have our weight coming down here, and it should be clear to everybody that because this thing is accelerating down, this has got to be bigger than the force of tension, and so we'll just draw that arrow a little longer. So notice now every aspect of these diagrams are correct. We have the tension forces being equal in these two diagrams. M2, the hanging mass, in this particular example, because they said that that one is 35 kilograms and the other one is 15 kilograms, M2G is larger than M1G. And then the normal force is the same length as the weight, because it should be, because this object is on a flat horizontal surface. And that surface is not like in an elevator accelerating up or down. So the equation for M1, as it turns out, is very easy. Because according to our scheme for writing the equations, we said you take MA and you set it equal to the forces going in the direction of the acceleration, which would be the tension, minus all the forces going in the opposite direction. And because there are no forces going in the opposite direction here, that's it. It should be pretty clear that when we get to talk about friction, that's going to be the main difference between the frictionless case and the case where there's friction. Moving on, for M2, we see here that we got to use the same scheme here. We take MA, M2A, and we set it equal to the force going in the direction of the acceleration, M2G, minus the force going in the opposite direction, which here is the tension. And there's our equation for M2. Now, as we mentioned, the main method of analysis is exactly the same. And when we were talking about the ATWOOD'S machine, we said the key thing to notice is that in the equations, because the tension of the rope is the same value, and like the objects are sort of going to be reacting to that tension differently, the tension is always going to have a different sign in these equations. In the one equation, it'll be positive, and in the other equation, it'll be negative. And so the best way, I think, to combine these equations is to add them. Now, you don't actually have to do it like this. You could do it however you want to. The question says determine the acceleration of the system and determine the tension in the rope. And so if you wanted to do the tension first and then solve for the acceleration, you can do that. You don't have to solve it by adding the equations either. You can solve it by substitution. But in my view, the easiest way to solve it is just to add these equations. And so what I'm going to write here is the acceleration is our unknown. I'm going to write M1, which is the mass on top of the table, is 15 kilograms. And I'm going to write M2 is 35 kilograms. And I'm going to take these equations and I'm going to add them together. So my equation for M1 was M1A equals the tension, right? Remember, we had that over here. And my equation for M2 is M2A equals M2G minus the force of tension. So we'll have M2A equals M2G minus the force of tension. And I'm going to take those equations and I'm going to add them together. And so when I add those equations, on the left-hand side, I get M1A plus M2A. And that's equal to, notice the tensions cancel, so I just have M2G. That's it. Now, solving this for the acceleration, it's not that complicated. On the left-hand side, I already have both terms that have the acceleration in it together, so all I need to do is factor out the A. So I have A times M1 plus M2 equals M2G. And that means when I solve this for A, all I have to do is divide both sides by the sum of the masses, so I get A equals M2G over M1 plus M2. And that's it for the acceleration equation for the system. So notice, by using the free body diagrams, we essentially just made that equation up. Now, I am going to revisit this with some notes here afterwards, but I just want to point out an important point here, which is notice that when we were talking about the regular ATWOOD'S machine, we said the acceleration always takes the form F net over m. Look at the numerator of that equation. What does the numerator of that equation suggest the net force acting on the system is? Doesn't that make sense? And then, of course, the mass. Look at what the denominator suggests the mass of the system is. Doesn't that make sense too? The key thing to realize is a lot of these things make sense, in my opinion, if you think about them. Again, we'll revisit that in a couple of minutes, so we might as well just finish what we're doing here, which is to solve for the acceleration. So we have M2, 35 kilograms, times G, which I should probably add to my list of knowns here, 9.8 meters per second squared. Notice sometimes if you forget that, you could just go back up and add it. G, 9.8 meters per second squared, over M1 plus M2. And so that's going to be 35 kilograms plus 50 kilograms. Oh, no, I did the math already in my head. 35 plus 15, which is going to be 50. So that's 35 kilograms plus 15 kilograms. Okay, so when you do that math, you basically have 35 over 50 times 9.8. And when you do that math, you get that the acceleration is 6.87 meters per second squared. Okay. And just to wrap this one up here, now we've been asked to solve for the tension as well. And so let's go ahead and solve for the tension. Notice now you have two options as to which equation you can use to solve for the tension. And I think it should be pretty obvious to everybody that one equation is much easier to use to solve for the tension than the other. And that would be the first equation, m1a equals ft. So just moving this on to the next slide, solving for the tension, we have the tension is equal to m1a. And so we get the force of tension is equal to m1, which was the mass on the table, 15 kilograms, times the acceleration, 6.87 meters per second squared. And that gives us a tension of 103.05 newtons. And so let's just call that 103. Yes, that has three significant figures. Don't worry about it. We're not going to go nuts about this. We'll just call it 103. And that's it for this problem. We solved for the tension and we solved for the acceleration. Notice, if we use the equation for m2, we would have gotten the same answer for the force of tension. Now, let's just take a second to address what I said I was going to address before. A equals m2g over the sum of the masses, m1 plus m2, is taking the form A equals F net over m. And so what that tells you is the F net in this problem is m2g, the weight of the hanging mass. That makes sense, because it is the whole fact that that mass is hanging and the force of gravity is pulling on it that makes the whole system move. Additionally, we can say that m here is the sum of the masses, m1 plus m2, which is just the total system mass. It's a very important thing to realize here that every time we write a free body diagram, come up with the equations, and then use those equations to solve for the acceleration, that equation for the acceleration is always taking the form of Newton's second law, A equals F net over m. And the reason why it's very important to realize that is because it'll help you answer conceptual questions. Take a second to pause this video here and write that down. And when you hit play, we'll take a look at some conceptual questions. Okay. So let's take a look at some conceptual questions. Here, this problem says, suppose we changed the mass of the object we're calling M2 to 30, let's say 230 kilograms. This is backwards here. It says 235 kilograms from 30, but it was 35. So let's say we're changing it to, you know what, let's actually change it to 40. Let's change it to 40 because I think that'll make sense here. Yeah. So let's say we are changing the mass of the object we're calling M2 to 40 kilograms from the previous 35 kilograms. Our question is, does the acceleration of the system increase, decrease, or remain the same? Take a second to think about that here. Does the acceleration of the system increase, decrease, or remain the same? Take a second to pause this video and try to work that out in your head. And when you hit play, we'll go over it. Okay, so what's complicated here about this particular problem is that in this case, it's all about ratios. And so you have to be careful. The reason why you have to be careful, and let me just go ahead and go back to the picture showing you the setup here. The reason why you have to be careful is because if I change the mass of M1, then the problem is not that hard because M1 is contributing nothing to the force acting on the system. It's only making the system more massive. And because it's making the system more massive, then all it does, notice, if you change M1, all it does is make the denominator bigger. And if we make the denominator bigger, then the acceleration is going to get smaller, and that makes sense. We're basically keeping the same net force, but we're increasing the inertia of the system, thus reducing the acceleration. But when we change M2, we have to be careful. And the reason why we have to be careful is because we are both changing the numerator and the denominator. M2, or I should say the weight of M2, is the force that is responsible for pulling the object, making them accelerate. It also contributes to the inertia of the system. And so we have to be mindful of both of those things if we're going to account for this properly. And so what you need to do, and this is the note we're going to write about in a second here, we need to think about the ratios. So essentially what happened here is that the numerator went from 35 to 40. And in the denominator, instead of being 35 plus 15, it went to 40 plus 15. And so the way that you can work this out here is pretty simple. You have to look at how the numerator and the denominator are going to change. The numerator now is going to be M2G. So instead of being 35 times G, it's going to be 40 times G. So what would be helpful is thinking about how many times bigger 40 is than 35. And so what we see here by doing this math, 40 over 35, is that the size of the numerator increases by a factor of 1.14. So we can write that down here. The numerator goes up by 1.14. And the question is, how does the denominator change? So in the beginning, we had 35 plus 15, so that was 50, right? And now we're going to have 40 plus 15, which is going to be 55. And so what we want to see is how much bigger 55 is than 50. And notice we see it's only 1.1 times bigger. And so because the numerator gets 1.14 times bigger when we increase the mass, but the denominator only gets 1.1 times bigger, what we see, and we can confirm this just by doing the math, what we see is that the overall acceleration gets slightly larger. Only a teeny bit larger, but larger nonetheless. Now, of course, you could just go over and solve this whole thing over again. right? Plugging in the masses, calculating the acceleration, whatever. But the point is, if they don't give you numbers and they just say it increases, you have to be careful. And I think the basic idea is, because it's just M2 in the top, but it's a sum in the bottom, you'll always see the top, the numerator, increase more by a larger factor than you'll see the bottom increase or the denominator increase. And so that's an important thing to realize. Thinking about ratios is going to be important here. And this particularly comes into play when we ask another good question, which is not does the acceleration of the system increase, decrease, or remain the same, but does the tension increase, decrease, or remain the same? And this is something we really need to talk about. And we want to talk about this very carefully, not just for this exact question, but for all questions. So let's just generalize. And the way that we'll generalize is we'll just play with the simulator. So let's say, and let's preserve the ratios here. So let's just divide them both by 10. So the mass that was up here on the table was 15 kilograms. So let's make that 1.5 kilograms. And we'll make M2, the hanging mass, which in this sim is called M1, we'll make that 3.5 kilograms. So notice, because the ratios are the same, we should see the same acceleration. Notice 6.86 is what they show here. That should be 6.86666 repeating, so they should have rounded that, but they didn't, but it's okay. So they show us the same acceleration, but of course, because the actual masses are different, the tension is different. And so in this case, the tension is only 10.29. That should also make sense, though, because we cut the masses by 10, we divided them by 10, the tension gets cut by 10. Okay. So what we said here was that we wanted to see how increasing the mass would change the tension. Notice here they're saying that that's 10.29, and if we increase it, it makes the tension go up. That should make sense. Right? Because now we have a heavier mass that's hanging. And so because we have a heavier mass hanging, it should make the tension go up. And what's important to realize here is we can, this part's very important to listen to, you have to be very careful. We can, in that instance where the hanging mass changes, we can use this equation. And the reason why we can use this equation is because the mass of object 1 doesn't change. And because the mass of object 1 is constant, we can see that by changing the mass of the hanging mass, we made the acceleration go up. And so the fact that the acceleration went up should make the tension go up. Notice we just predicted before that if we changed the mass from 3.5 or 35 to 40, 3.5 to 4 in this simulator, then it should make the acceleration go up because the numerator increased by more than the denominator, right? And notice when we do that, it does make the acceleration go up. And the fact that the acceleration goes up makes the tension go up. Now, of course, the question is, well, why the heck am I talking about this? And the reason why I'm talking about this is because you have to be really careful when the thing you're changing is M2, the mass of the object on the table. The reason why you have to be careful is because let's say we increase it. If we increase it, notice increasing the mass, everybody look at the acceleration measurement here. Increasing the mass actually makes the acceleration go down, but it makes the tension go up. And that's confusing because this equation, Ft equals m1a, suggests that the acceleration and the tension change together. And here we see that they're actually doing the opposite. It makes sense if you think about it, but you got to be careful. Number one, it makes sense that it makes the tension bigger because basically now instead of letting M1 experience free fall, M2 is resisting it being in free fall. And so that makes the rope experience a larger tension. But because M2 is just sitting on the table and its weight is not contributing to the net force, it actually makes the acceleration go down because there's more inertia in the system. And so what we want to say here, again, is that since the acceleration is dependent on the tension, and not the other way around, we can't use the equation Ft equals m1a to determine the change in tension when the mass on the table changes. So when the mass on the table changes, we want to think in terms of ratios. And we're going to wrap this up by talking about that as soon as you write this down. So take a second to pause this video here and write that down. And when you hit play, we'll move on. Okay, so the basic way that you consider changes in the tension is you solve for the tension and you look at what the equation says. So notice we had two equations here in this last problem. We had Ft equals m1a, and we had the equation for the hanging block, which was m2a equals m2g minus the force of tension. And if we want to solve this for the tension, we got to get rid of the acceleration. So what we should do is we should solve both equations for the acceleration, and we should set them equal to each other, because then we'll get rid of the acceleration in the equation. And so if we take these equations, both set equal, both solve for a, and we set the accelerations equal to each other, we get Ft over m1, that would be this equation, equals m2g minus the tension over m2. And to solve this for the tension, the first thing we got to do is just make this not a fraction. So we cross multiply. We bring the m1 over there, we bring the m2 over here. So on the left-hand side, we get Ft times m2. And on the right-hand side, we get m1 times m2g, because we got to distribute this thing. And then we get minus Ft times m1. And I got to basically group my like terms, factor, and do all that. So the first thing I got to do is I got to add the tension to the other side. So I have Ft m1 plus Ft m2 equals m1 m2 g. And then when I factor, I'm going to pull out the Ft and I'm going to have m1 plus m2. And so when I solve this for the tension, I'm going to have m1 m2g over the sum of the masses m1 plus m2. There's my equation for the tension with no acceleration in it whatsoever. So what we can see is that the tension is directly proportional to the product of the masses, and it's inversely proportional to the sum of the masses. Now, how does that play itself out when we look at an actual example? Well, if we look at an actual example, and you'll see, let's say, as we did before, let's say we have our situation where we had 35 and 15. Of course, we're scaling these down because the largest we can make a mass here is 10 kilograms. So we'll have them be 35 or 3.5 and 1.5 to represent this situation we had originally. And let's say we increase the mass. Again, what's complicated about using just the equation Ft equals m1a is because that equation suggests the tension is directly proportional to the mass. So the fact that we increase the mass should increase the tension. But that equation also would suggest that the tension is directly proportional to the acceleration, which, if you noticed, was 6.87 and is now 6.24. So that went down. Now, let's just use our heads here because this is not that complicated. Notice the tension was 10.29, and now that we increased it, it's 12.47. So increasing the mass on the table does make the tension increase. The question here is, how can we use an equation to confirm that? Well, according to the equation, the tension is directly proportional to the product of the masses and inversely proportional to the sum of the masses. So let's look at the product first. In the beginning, the masses we had were 3.5 and 1.5. So 3.5 times 1.5 is a number. That number happens to be 5.25. But now we've changed that to 2. And so notice the numerator here is going to go from 5.25 to 7. And 7 is bigger than 5.25 by a pretty good amount. It's bigger than it by a third, essentially, 1.3333 times bigger. Now, if we look at the sum, we're not going to see that big of an increase, because if we take 3.5 plus 1.5, you know the answer here is going to be 5. And if we take 3.5 plus 2, we're going to get 5.5. And so now the denominator is only bigger than the old denominator by a factor of 1.1. And so if by increasing the mass on the table, if we've increased the size of the numerator in the equation for the tension force by 1 1/3, but we've only increased the denominator by 1.1, that means the overall tension is going to change by a factor of 1.2. And notice the original tension was 10.29. And if we take 10.29 times that number, then we get 12.47. And notice when we increased the mass to 2, we got 12.47. So the fact that the numerator is a product and the denominator is a sum means in that case the numerator increases faster or at a larger rate than the denominator, which means changing that mass makes the tension go up. And what's a little complicated with that is you can't quite use the equation Ft equals m1a because, number one, the acceleration is dependent on the tension, and the tension is not dependent on the acceleration. And number two is that even if you ignored that fact, looking at the tension being directly proportional to the mass and directly proportional to the acceleration, one of them increases and the other decreases. And so you got to be careful about it. And the way to do that is by using those equations and thinking about the ratios. All right, so the last thing we want to do before we go today is talk about a problem, which is really the last problem that we have to deal with when there's no friction. And this kind of problem I generally refer to as the connected objects problem. And so the connected objects problem is pretty simple. You have two objects which are tied together with a string. And in front of the first object here, there's another string which somebody is going to pull on. Now, technically, because somebody is pulling on a string, this is a force of tension, but because somebody, like a person, is actually going to have to come and pull on the string, we generally refer to that as the applied force, which we usually label F applied, or like FA or FAPP for F applied. And so somebody's going to apply a force, and these objects are going to move. And what I would like you to do is I would like you to solve this problem. Now, we're going to do this in stages, but the first thing that you definitely have to realize here is that the way we are going to solve this problem is the way we solve every other problem in this unit. We are going to draw the free body diagrams. We are going to write the equations from the free body diagrams, and then we are going to combine those equations to solve for what we are being asked to solve for. And so in this particular problem, let's say the setup generally was like this, where we had an applied force, a force applied to the object of 30 newtons, and we had these two masses here. This one that's in front, like the first block that's next to the applied force, we usually call M1, and we're going to say that that's 15 kilograms, and we'll say the mass of the second block, the smaller one here, is going to be 10 kilograms. Like I just alluded to here, the first thing that we have to do when we're solving this problem is we have to draw the free body diagram. So the first thing I'd like you to do here is draw the free body diagram for this particular situation. So I'd like you to take a minute to pause this video here and draw the free body diagram. And when you hit play, we'll go over it. Okay, so it's important to realize here, before we just go ahead and show the drawing, that because these objects are connected by a string, there's going to be a force of tension here. And that's generally why we refer to this as F applied instead of a force of tension, so we don't mix them up. And so we'll start with M2. And so M2 is the object that's in the back here. It's 10 kilograms. And so we'll draw our object here, and we'll draw the dot at the center of the object. And the key thing to recognize when you're drawing these diagrams is that both of these objects are going to end up accelerating to the right due to this applied force. So this object is going to end up accelerating to the right. And so we'll include that off to the side. Now, why is this object going to accelerate to the right? Well, that's because it has a force of tension acting on it to the right. So we'll draw that in here. And of course, because this object, and I'm just going to go back, is shown to be sitting on some surface, it has a weight acting straight down. Obviously, that's because it's on the surface of the Earth. And because it is on like a table or the ground, it has a normal force, which is equal and opposite of that weight. It's because it's on a flat horizontal surface, and so we'll label that F with the subscript N. And there's our free body diagram for M2. For M1, we have a slightly more complicated picture, but not all that complicated. Again, like we did for the last one, we should recognize here that this object, M1, is going to be accelerating to the right. And that's really the first thing you want to focus in on. And the reason why you want to focus in on that is because there's not just one force acting to the right anymore. There are two forces that are acting, one to the right and one to the left. And that's what makes this different from the diagram for M2. Now, it should be clear to everybody that if this block, M2, has a force of tension acting on it to the right, then this block is going to have that same size force of tension because the tension is constant in the rope, but that's going to be acting to the left. That tension force in the rope is going to be pulling the block that's in front back a little bit. And that's basically just because M1 is responsible for pulling on M2 to make sure that M2 moves as well. Now, of course, if the question is, why am I talking about this? It's because, number one, you want to show these arrows the same length, and they're approximately the same length. Again, we're not taking out a ruler, but they should be shown as being the same. And also because that means whatever arrow you draw for the applied force, it's got to be longer than the arrow for the force of tension, because the net force, when you combine these two forces, has to be to the right in order to enable this thing to accelerate to the right. So there are forces on the left-right axis, so to speak, And then in the vertical direction, we have the weight, which notice we now want to draw this arrow bigger than the weight arrow for M2 because this one has more mass. And then when we draw the normal force, we want to make that as long as our arrow for M1G. And these are the diagrams for both blocks now. And so again, to write our equation, we take MA, and because this is M2, we'll call it M2A, and it's equal to the forces going in the direction of the acceleration, Ft, minus the forces going in the opposite direction. Since there are no forces going in the opposite direction, that's it. We have M2A equals Ft. Additionally, for the block M1, we have M1A equals the forces going in the direction of the acceleration, which is F applied, and then we subtract the forces going in the opposite direction, Ft, the force of tension. And there's our equation for M1. And now, for the first time we're looking at this problem, I'm going to ask you the same question I asked you when we looked at the other two problems for the first time. What do you notice about the structure of these equations that might make it easy to solve this problem? And the key thing to notice here is that in the equation for M2, we have the force of tension, and because the tension is always acting in opposite directions when we're talking about these two objects which are connected by the string, the tension in this equation is negative. And that means it's going to be very easy for us to combine these equations by adding them. And so again, let's just go ahead and solve this problem for the acceleration, and let's solve for the force of tension. And so the first thing we're going to do is we're going to go ahead and solve this for the acceleration. And so to solve this for the acceleration, the best thing to do is to add it. And so we'll say here that M1, just to remind ourselves, is 15 kilograms. M2 is 10 kilograms. G is 9.8 meters per second squared. We're looking for the acceleration, and we're looking for the force of tension. So first, we'll write our equation for M2. We had M2A equals Ft. And for M1, we have M1A equals the force applied minus the tension force. And when we add those equations, you can see the tensions are going to cancel. That's what we want to get the acceleration to be the only unknown in this equation. And we'll have M1A plus M2A equals F applied. Pretty good. And we'll go ahead and solve this for the acceleration. To do that, we have to factor out the acceleration. So we have A times the product of the mass, or the sum of the masses, excuse me, A times the sum of the masses, M1 plus M2. And then that's equal to F applied. And so to solve this for the acceleration, all we have to do is divide by the sum of the masses, M1 plus M2, and we get A equals F applied over the sum of the masses. We'll write a note about this in a minute, but it's important to realize the structure of this equation for the acceleration always takes the form of Newton's second law. And that tells us something pretty interesting about what the net force acting on this system is, what the total mass of the system is, right? So when we plug in these numbers here, we have the applied force, which is 30 newtons, over the sum of the masses, 15 kilograms plus 10 kilograms. And so 15 plus 10 is 25, and 30 over 25 is 1.2 meters per second squared. And that's our acceleration. And because we have room over here, we could just show this over here. Now, to find the force of tension, again, you can use either of these equations, but it makes most sense to me to use the equation for M2, because that equation just says Ft, the force of tension, equals M2A. And so we have the tension equals M2, 10 kilograms, times the acceleration, 1.2 meters per second squared. And that gives us a tension force of 12 newtons. And that problem's not all that hard to solve. Now, you will see, again, like we did for the tabletop ATWOOD'S machine, once we talk about friction, we will go back and revisit this. But since there are a lot of examples of these on frictionless surfaces, it's good to know how to solve both ways. Now, before we go, we want to just talk about some big picture concepts and some hints and little tricks. The first thing to realize is what we were saying over here. Every time we solve a free body diagram equation for the acceleration, it takes the structure of Newton's second law. And so what that means is that since all equations for the acceleration will take the form of A equals F net over M, for the connected objects problem, you can always just treat the objects as a system, where you essentially just imagine the two objects as one object with a mass equal to the combined mass of both objects. That's the idea here. And notice when we do that, if you look at the acceleration equation that we just came up with, it basically is just imagining the problem as the applied force of 30 newtons being attached to just the one 25 kilogram object. Now, obviously, there's not just one 25 kilogram object, but we can treat the two connected objects as having a total mass equal to the sum of their masses. Take a second to pause this video here and write that down. And so notice when you do that, you'd realize the 30 Newton applied force acting on that one 25 kilogram object would give you an acceleration of 1.2 meters per second squared. And then all you need to do, let me just go back here, all you need to do to find the force of tension is to just say, well, the rope, and I'll go back to the free body diagram, the rope is the only thing that's pulling on M2, and so that's the force individually that's responsible for its individual mass's acceleration. And that's it. Now, another interesting thing to realize, and this I think is very cool, another interesting thing to realize is that you could either, after treating this thing as a system, to just solve for the acceleration that way, realizing that the only applied force on the system is the net force. After you solve for the acceleration, you could use a very interesting little trick. And that'll be the last thing we talk about for today. And so we'll write this as a note. Note, let's see what the ratio of the applied force is to the tension. The applied force was 30 newtons. The tension was 12 newtons. And when you do that, you get 2.5. The applied force is 2.5 times bigger than the tension. And then we ask the question, well, what mass is the applied force responsible for moving? Both M1 plus M2. What mass is just the force of tension on that in-between rope responsible for moving? And that's just responsible for moving M2. And if we take M1 plus M2, which is 15 kilograms plus 10 kilograms, and then we just take M2, which is 10 kilograms, that gives us 25 kilograms over 10 kilograms, which is also 2.5. These ratios are equal. And so we'll write here, these ratios are always equal when there's no friction. And that's because whether you're considering the applied force acting on the whole system or just the tension force acting on M2, the acceleration of the system is equal to the acceleration of object 2. And so, if you were given this exact problem, where instead of them asking you what is the acceleration, they just asked you what the tension was, you can just say, what's the ratio of the masses? Oh, the total mass is 2.5 times bigger than the mass of the second object. And then say, well, the applied force just got to be 2.5 times bigger than the tension. And figure out the number that way. Nice little shortcut for multiple choice questions. And with that, that's it for today. As we mentioned, tomorrow is Veterans Day, so we have no class. And on Thursday, we will take a look at friction and how we will use friction concepts to solve problems. All right, everybody. Have a good one.